We would like to prove the formula for vector projection. Imagine you have two vectors A and B, and you have a big lamp that shines a light on A so that it casts a shadow at 90 degrees onto the B vector. Now imagine a new vector that's just the part of the B vector which is in the shadow of the A vector. We'll call this A onto B. This is a projection vector. But if you know A and B, how do you get the projection vector? The first thing you need to realize is that it's just a scaled version of the B vector. You know that by multiplying a vector by a number you can make it shorter or longer, and if you multiply B vector by the right number you can make it exactly the same as the projection vector. So you need a very specific constant k to multiply with a B vector to get the projection vector. Finding the scalar k would solve the problem, and to do that we look at the dot product between A and B vectors. We can cleverly rewrite the A vector if we come up with a new vector called c, and it's just an orthogonal vector to the B vector. You'll see why in a moment. Notice that if you add c and the projection vector, you get the A vector. So instead of A, let us write c plus the projection vector. This is the dot product. You're allowed to distribute the B vector inside of the parentheses. This gives you the term c dot b, which equals 0 because they are orthogonal. Remember that the projection vector can be written as a scaled version of the B vector, and if you insert that you have the dot product of B with itself, which gives you the magnitude squared of B. Now isolate the constant k and insert it into the argument from earlier, and you get the projection vector formula.